Section 5.5 orthogonal set. We consider inner product space V and n vectors in this space V1, V2 to Vn. We call this set is orthogonal if for each pair Vi and Vj they are orthogonal each other. Let's further consider a set of vectors v1, v2 to Vn. If this set is orthogonal, and also each of the vectors here has next 1, then we call this set is a orthonormal set. Let's compare these two definitions. For the first definition about orthogonal sets, we assume here each of the vectors is non-zero. But for the second one, we don't need to assume each of the vector is zero non-zero, because when we require the negative one, for sure none of these vectors v1, v2 to Vn is 0. So from this we can see the difference between orthogonal and orthonormal. Orthonormal is orthogonal plus next one. Example 1. In this case, V is the set of continuous function from negative pi to pi, and the inner product is defined by this integral. First of all, we can say this set here. The first vector is 1, second is cosine x, then cosine 2x to the cosine nx. This set is orthogonal. Why? Just by the definition. We look at the inner product. For the first vector v1 equals 1, and the other vectors cosine kx, the inner product by definition here is the integral. So we substitute f of x by 1 and then gx by cosine kx. Sorry, this should be cosine kxk. Cosine kx take integral, the antiderivative will be 1 over k sine kx. So that value is 0. So this part is incorrect. We will change it. And then we consider cosine kx and cosine jx for k not equal to j. Then by definition, the inner product is given by this form. Then we can find the antiderivative for this integral, and we can say the value is 0. So that means in this set, each pair, they are orthogonal, so that the whole set is a orthogonal set. Now we consider the second set. Now what's the difference between these two sets? We can say the first vector are not the same. The first vector for the first part is 1. The second is 1 over square root n. 1 over square root 2. And then the rest are the same. Now in this case, we can show this set is orthonormal. Why? First of all, is orthogonal. Orthogonal, we can use the same way to verify. And then what we need to do is look at the next for each vector. So for the first vector, the function is 1 over square root of 2. So the inner product here equal to 1 over pi, then integral here should be 1 over square root pi, 1 over square root 2 times 1 over square root 2, then that gets the 1/2. Now, in this case, we can say this integral here equal to 2 pi, and then cancel the word with 1 over 2 pi and 1. So the next, for the first vector here is 1. Then for the rest vectors, say cosine kx, we can evaluate its length. That's by the definition of inner product. That's 1 over pi times integral from negative pi to pi cosine square kx. The antiderivative here is here we can easily find after we use the formula from cosine function. Now, cosine square kx equal to 1 plus cosine 2 kx over 2. And then for this function, we can easily find its antiderivative. And actually, we can say this integral here equal to pi, so that the whole value or the next of cosine x equal to 1. So put together, we can say this set is orthonormal. Theorem 5.5.1. If V1, V2 to Vn is a orthogonal set of non-zero vectors in the inner product space V, then these vectors are linearly independent. Now, here there is an important assumption. We assume the set here, each of the vectors are non-zero. If there is one of them is 0, then we cannot get these vectors are linearly independent. How to prove this theorem? The idea is simple. We just use the definition for linear independence. So to do this, we start from this equation. Here, C1 times V1 plus C2 times V2 to the CK times Vk plus Cn Vn equals 0. Then here, both sides we consider the inner product with vector Vk. From this, you can say why in the middle we have this term CKVK. The reason is we want to take inner product for each side with the vector Vk. And then we can say here, when k not equal to 1, then V1, V2, V1, Vk, the inner product is 0. So for the first inner product get 0, second get 0, only in the middle here, Ck and Ck times Vk make inner product with Vk. In this case, we can move the constant Ck to the front and get the inner product of Vk and Vk. Then the rest inner product at 0. The right side is simple because that's the linear product between 0 and vk. That's 0. So in this way, we got ck times the next of vk squared equals 0. Recall vk is non-zero, so its next is not 0. Then for that, or for this equation to be true, ck must be 0. Now this, we can assume k is any of these integers from 1 to n, so that we got what? We got if this equation holds, then each of these scalars c1, c2 to cn must be 0. Must be 0 by the definition. We know v1, v2 to vn are linearly independent. Based on the theorem 5.5.1, we can have a definition we call orthonormal base. We say vectors u1, u2 to un form a orthonormal base of inner product space V if it satisfies the following two conditions. First of all, u1, u2 to un form a base for the inner product space V. And the second assumption is this set here is orthonormal set. One may ask why we prefer orthonormal base. Now, the reason for this is because once we have a orthonormal base, then we can easily calculate the coordinates for a vector v with respect to orthonormal base. Here should be orthonormal, not just orthogonal. Recall, orthonormal means we have first orthogonal, then next one. Theorem 5.5.2. If we are given a orthonormal base for an inner product V, for example, the base here is u1, u2 to un, then for each vector V in the inner product space, we can represent this vector V as a linear combination of the base. And more precisely, we can say the coefficient here is just equal to the given vector V and with each of the vectors in the base, the inner product. So from this, we can say the representation is relatively easy. In the sense, once we have the vector V, then we just need to evaluate the inner product of V with each of the vectors in the base inner product. Then we can get a representation for the vector V. The proof for this theorem is quite simple. First of all, we can write down V as a linear combination of, this should be summation Ci times Ui, because Ui here is the base we are talking about. So CIUJ. The reason why we can write down this is because U1, U2, Un is a base for the vector space V, so that each vector in the vector space V can be written as a linear combination of the base. Then both sides we take inner product with the vector Vk. Sorry, this should be Uk, not Vk, because we assume here the base is U1 to Un. So in this way, we take the inner product and with UK. Then because we assume U1, U2 to Un here is the set of orthonormal base, so that we can show, or we can say CK has to be equal to the inner product between V and the UK. The reason for that is the inner product of UJ with UK equals 0 if J and K are not the same. So in this way, we get CK is just the inner product between V and UK. And in this way, we can say this representation, in particularly, we got the coefficient here is just the inner product between V and UK. Corollary 5.5.3. We assume U1, U2 to Un is a orthonormal base for an inner product space V. In this case, let's consider two vectors U and V, because we got the orthonormal base, so that we can write down U as a linear combination of the base. And similarly, by the theorem just proved, we can write down V as a linear combination for the base. Then we can show, in this case, calculate the inner product between U and V is just equal to this kind of sum of coefficient products. So that's AK times BK. Here's the proof. The inner product between U and V. So U equal to the summation of AK UK. So that's the first term. Similarly, for the V, that's the second term. And then we use the definition for inner product. We can say, in this case, we can get the coefficients AK, sorry, this should be BJ, AK, BJ out. And then make the inner product between UK and UJ. Because we assume U1, U2 to Un are orthogonal, so that when K and J are the same, then the inner product is 0. So that means we just need to consider here when K and J are the same. In that case, we got the summation here, the double summation becomes a single summation. So K from 1 to N, then AK, BK. Then here we should have the inner product between UK and UK. That is 1 because we assume here the base is not just a base but also orthonormal. That means each of the vectors here has the next one, so that we get the inner product between u and v equal to this form. Now from this we can say once we have a orthonormal base, then take the inner product is relatively easier. That we just need to make the product like this. Now we consider a particular case. If, for example, u and v are the same, when u and v are the same, then we can say ak and bk are the same. So in that kind of case, here we can say the inner product will be equal to the square root of x of u. So from this, we can easily get corollary 5.4. Now, this formula, there is a name is called Parseval's formula. Let's take a look at example 2. Here we assume u1, u2, u3 is as orthonormal base for inner product space V. And we assume u equal to this form and V has this form. We want to find the inner product between u and v and the length of each of these two vectors. Then we want to find the angle between u and v. To evaluate the inner product between u and v, we can use the corollary 5.5.3, or we just take a look at these two vectors. So the inner product, we should go one by one. But here, because u1, u2 to u3, they form a orthonormal base, so that the inner product here is just the coefficient make the product. So that should be 3 times 4. Then 2 times here the coefficient -3. Then we should plus 1 times 0, because here if we make up, then we should plus 0 u3, but that's just 0. So we can say here the inner product between u and v equal to 6. Then we can find the length for u and v. So that is just based on corollary 5.5.4. We just take a square root of the coefficient here. So that's 3 squared plus 2 squared plus 1 squared. So that's the answer. Similarly, for the vector v, we can calculate its length. That is square root of 4 squared plus -3 squared. And for that, we get the length of v equal to 5. So essentially, when we have a orthonormal base, then calculate the inner product and the length is just like when we did in Rn. in Rn, we talk about scalar product. So that kind of calculation now we can apply it in the case we have a orthonormal base for a vector space. So the idea here, the calculation is similar to what we had for the scalar product in Rn. All right, so next we need to evaluate the angle theta between u and v. By the formula, the theta equal to arc cosine of this quotient. Now we have the inner product here, that's 6, and then we have the next. Then we get this value. And the arc cosine for this quotient, that's the angle theta between u and v. Example 3. We assume u1, u2, and u3 form an orthonormal base for an inner product space. And here we have a vector x. This vector x belongs to the inner product space, and it has this representation in terms of the orthonormal base. We are given the length of x is 8. X is orthogonal to u3, and the inner product between x and u2 equals 2. What we require is to find these three coefficients, C1, C2, C3. Now, let's find the solution. First of all, we can say between the inner product between x and u2 equals 2. So from the theorem we proved earlier, we can say this coefficient is just the inner product between x and u2. So that we can say C2 equals 2. And then by this assumption, x and u3 are orthogonal, so that the inner product between x and u3 is 0. That means this coefficient here is 0. Now, once we get the value of C2 and C3, then let's use the first assumption here, which means the length of x is 8. We want to find C1. So in this case, we can say the length of x is 8, so that both sides we take a square. Then we got 8 squared equal to the length of x squared. Then the length of x equal to the square root of the coefficient squared, so that the sum of coefficient squared, so that we get this square equal to C1 square plus C2 square plus C3 square, based on the corollary 5.5.4. That's Parseval's formula. And we just say C2 equal to 2, so that's this term. And then C3 is 0, so we get C1 square plus this is 2 square. Then we want to find the C1 squared, so that we move this term to the left, so that we get C1 squared equal to 8 squared minus 2 squared. 8 squared is 64. 64 minus 4 is 60. So that we got C squared equals 60. That means the two possibilities for C1. C1 equals positive square root of 60 or negative square root of 60. So in this way, we got the values for C1, C2, and C3. Orthogonal matrix. Here we consider an n by n matrix Q. Now this is a square matrix. We call this matrix is an orthogonal matrix if its column vectors form a orthonormal base in Rn. Somehow it's a little bit hard to say how to show a matrix Q is orthogonal, but we have some equivalent conditions. Here we have theorem 5.5.5. The theorem tells us a square matrix Q here is orthogonal if and only if the transpose of Q times Q equals the identity matrix I. So that means if we want to show a matrix is orthogonal, we just need to check whether or not this equation holds. How to prove this theorem? We start to write the matrix Q in terms of its columns, because we assume the Q is n by n, so that this Q matrix has Q columns. We call it Q1, Q2 to Qn. Then by the definition here, Q is orthogonal. By the definition, that requires its column vectors form a orthonormal base in Rn. What's the definition for orthonormal? Orthonormal, we need two conditions. First of all, each pair Qi and Qj are orthogonal each other. The second condition is each of the vectors here has maximum. So this is the same as when we look at the inner product between Qi and Qj, we can say this inner product equals 0 if I and j are not same. That's actually because Qn and Qj are orthogonal. So the scalar product equals 0 when I and j are not same. Then when I and j are the same, that means here we talk about the same vector, Qi and Qi make the inner product or scalar product. That's equal 1. So we got this form for the inner product between Qi and Qj. Then we can say this is equivalent to we calculate the product between the transpose of Q and the Q. Recall, we assume the Q equals this form, so that we take the transpose of Q, then we got this form. So this is the first column of Q transpose is Q1 transpose. So This is the first row for Q transpose, the second row for the Q transpose, and this is the last row for the Q transpose. And this part is the matrix Q. We made this assumption in the beginning of the proof. Then here we have one matrix and the second matrix. We calculate their product. So that should be Q1 transpose times Q1. So we get this term. And then Q1 transpose times Q2. So that's this term. Then Q1 transpose times Qn here. So that's the last term on the first row. Similarly, we use the second row. Look, this is the second row for this matrix. Second row times the first column, we get this is Q2 transpose times Q1. Then second row times the second column, that gave us this entry. So that's the Q2 transpose times Q2. And then Q2 transpose, or the second row times the last column, we get this entry. Do the similar way for all the rest. Then we can say here on the main diagonal, that's Q1 and Q1 make inner product. We know that's equal to 1. So this is 1. Similarly, this main diagonal entry here is 1. All the main diagonal entry, we can say the values are 1. Then for the rest, Q1 and Q2 inner product is 0. And all others of main diagonal, all the entries are 0. So that in this way we get this matrix here is n by n identity matrix. So in this way we showed the transpose of Q times Q equals n by n identity matrix. So that's the seal. Here are some properties for a orthogonal matrix. In this case, we assume Q is a square matrix, and Q is orthogonal. Then, by the definition for orthogonal, we know for the Q is column vectors form a orthogonal base for vector space Rn. Then for the second, based on the theorem just proved, or the theorem 5.5.5, we know the transpose of Q times Q equal to n by n identity matrix. The third property is the transpose of Q equals the inverse of Q. Why? Now, just look at this second property. We can say if both sides we multiply by the inverse of Q from the right side, then we get the Q transpose equal to the inverse of Q. And then we can get the determinant of Q equal to 1 or less to 1. We will show this soon. The fifth property is Q1 times the transpose of Q1 plus Q2 times the transpose of Q, and go this way, Qn times the transpose of Qn equal to n by n identity matrix. Now, this one you can say is the exercise at the end of this section. The property 6 is given two vectors x and y in Rn. We use q times x first and q times y first, then make the inner product. We can say this inner product equals the inner product between x and y. Now, this proof is simple because what? Because in Rn the inner product is the singular product. So this inner product equals the transpose of qx then multiplied qy. Then you can say that the transpose of qx equal to x transpose q transpose. Q transpose times q equals I because the second problem. So let me get this. The property 7 is the next of qx equal to the next of x. Why? You just in property 6 you take x y equal to x, then you can say the left side will be equal to the square of the next of qx, and the right side that is the square of the next of x. So both sides take square like this. Property 8. The angle between qx and qy equals the angle between x and y. Now this one we can say if either x or y equals 0, then that's the angle both sides equal 0. If both x and y are non-zero, then we can use properties 6 and 7. By taking quotient, we can get the angle between qx and qy is the same as the angle between x and y. So these are 8 properties for a orthogonal matrix. Let's just take a proof for property 4. First of all, because Q is orthogonal, so that by theorem 5.5, we know the transpose of Q times Q equals I. But here we write it down in a reverse way. We write it down I equals Q transpose times Q. The reason for this because we just want to make the following procedure looks easier. So what we do for this equation is both sides we take determinant. Then determinant of I, of course, that's equal 1. So 1 equal to determinant of I then equals the determinant of the right side. This is a product. So determinant of the product equal to take a determinant first, then make the product. But the determinant of Q transpose equals the determinant of Q, so that we get this. Then that means we got the square of determinant of Q. From this, both sides we take a square root. We can say the determinant of Q is equal to 1 or negative 1. So in this way, we proved property 4. Theorem 5.5.7. In this case, we consider an inner product space V, and S is a subspace of V. We assume U1, U2 to Un is a orthonormal base for this subspace. Now we consider a vector X. X belongs to the vector space V, but X may not belong to the subspace. Here, if we have a vector P, this vector P is a linear combination of U1, U2 to UK. The coefficient here, the CK, equals the inner product between X and UK. From this, we can say the vector P here, because P is a linear combination of the base for the subspace S, so that we can say the vector P here belongs to the subspace S. Given this condition, we can show X minus P belongs to the complement of S, or orthogonal complement of S. And we can write actually X equals P plus X minus P. Of course, this is true, because here we can say P plus negative P will get 0. So that this is a simple decomposition for vector X belongs to V. But more precisely, we can say this decomposition here is a direct decomposition for the vector X. Why? Because P belongs to S, and X minus P belongs to the orthogonal complement of X. How to prove this conclusion? Now, to do this, we need to use the definition for orthogonal complement. To show this vector X minus P belongs to the orthogonal complement of S, we need to show this vector is perpendicular or orthogonal to each vector Y. Y is a vector of S. So once we understand what we're supposed to show, then the proof is relatively simple. So here's the proof. First of all, we pick up an arbitrary Y from the subspace S. Then for the vector Y, we can represent it as a linear combination of the base of S. So we can write it down Y as the linear combination of UK. Then we calculate the inner product between X minus P and Y. Here we have X. X is a vector in V. Then minus P. P from the assumption has this form. So we substitute P by the summation. And then we have the representation for the vector Y, because Y belongs to S, so get this form. Then we make this make this inner product here. So that should be inner product between X and this vector Y. then minus this inner product P. So here we have two vectors, this vector P and the vector Y. Then we can say, based on the definition for inner product, we can say the inner product X and this summation here, that's equal to move the scalar BK out, and then make the inner product X and each of the UK. Then minus the second term with inner product of this vector Y. And recall we had the corollary 5.5.3. So that's the inner product between P and Y. And then from this, we can say here we have BK here, BK here, and then take a look. CK equals the inner product between X and the UK. That's the sum here. So that we get these two summations are the same. So that we get the value here is 0. That means X minus P is orthogonal to each vector Y in the subspace S. That means X minus P belongs to the orthogonal complement of S. So we proved the theorem. Theorem 5.5.8. Here we have the similar, or actually the same assumptions in theorem 5.5.7 we just proved. We assume V is the inner product space, S is a subspace of V, and we have this set is a orthogonal base for subspace S. We consider vector X belongs to the inner product space V. Assume P can be written as a linear combination of U1, U2 to Un. This means P belongs to the subspace S. Then the conclusion is P is closest to X. What means closest? We had this conclusion or this kind of term in section 5.4. P is closest to X means the length or the distance between X and Y is bigger than the distance between X and P. So in this way, distance is smaller means that's the meaning for P is close to X. We had a similar result in section 5.4. Now the proof of this is really simple. In this case, we call the vector P is a projection of X onto the subspace S. To prove this, we use a similar procedure just like what we did in the last section. So instead the proof for the distance, we take square because the square is relatively easy because the square of the length can be written as the inner product. So we consider square of the distance between X and Y. That's equal to the inner product between X minus Y and itself. And then here we make a simple algebra. We take away negative p and then add it up. Do the same thing for the second term. So we use x minus p and then plus p here. Why we use this way? Because we want to have x minus p term. So that's why we write down x minus p and then add p up. Then we got this here, we can say 1, 2, 3, 4, 4 times. So we look at term by term, look at the inner product. So inner product between x minus p and itself. So that's the first term with this first term here. And then x minus p with p minus x. And then we should have another term, so we get double. Then p minus y and itself inner product. Then the first inner product here equal to the square of the next of x minus p. The last term is the square of the next between p minus y. The second term here equals 0 because what? Because p belongs to S, y belongs to S, so that p minus y belongs to the subspace S. But we proved in last theorem x minus p belongs to the orthogonal complement of S, so that this inner product equals 0. So that we got one square term, the second square term, we drop the second term, we got greater than equal to this. If y is not the same as p, then here should take greater than sign, no equal. So in this way, we proved this theorem 5.5.8. Corollary 5.5.9. Here, we consider a vector b. B belongs to Rn. In this case, the projection P of B onto S is given by U times the transpose of U times B. Here, U is a K by K matrix. This is a K by K matrix. Its column vectors are U1, U2 to Lk. Now, recall U1, U2 to Lk is a subspace of R. Here's the proof. First of all, from theorem 5.5.7, we can say P here is a linear combination of the base for the subspace S. And this linear combination we can write it down as this kind of form. That's just like U1 times C1, so that's the first term. Then U2 times C2, and then UK times CK. So in this way, we can write down this summation as this kind of form. Then, because we assume the U is a matrix made by this K column vector, so that we get this is U, and then this is the C. But the C1 equal to the inner product between B and U1. That's from the theorem 5.57. So we get that. And this inner product equals the scalar product because we are in the space V is Rn, so that the inner product is the scalar product, so that this is the inner product or the scalar product between B and U1. We write it down like this. The reason why we write it down like this is because here we can say each entry here share with the same vector B, so we move this B out. In this way, we can say here this part it actually equals the transpose of U matrix. Because what? Because if here say U equals this matrix, we take a transpose, then U1 transpose will be the first row for U transpose. And similarly, the last row here is the last row of the matrix U transpose. And then we can say the C1, C2 to Ck, this vector equals transpose of U times B. So we do the substitution, then we get this. So this gave us a way how to find the projection of a vector P. That's the projection of vector B onto a subspace S. Let's take a look at an example for the last curve. The question is, we want to find the best linear square approximation to function e to the x on the interval between 0 and 1 by a linear function. To solve this question, first of all, we need a set of inner product space. Now, how to set inner product space here? Now, for this, we can say we have e to the power x. So this is for sure a function. This is a continuous function. And also, at the end, we say a linear function. A linear function also a continuous function. And then the function we want to talk about is on the interval from 0 to 1. So in this way, we can set up the inner product V as the set of continuous function on interval from 0 to 1. And then we need to introduce the inner product. So for two continuous functions on interval from 0 to 1, we define their inner product by this integral. After this, then we need to find a subspace. Let's call this subspace S. Then how to set up this subspace? Now for this, we can say at the end of the question, we ask by a linear function. So that means we should make up or set up a subspace S as the set of linear functions on interval from 0. So in this way, we consider S be the set of all linear functions on interval from 0 to 1. So this is the subspace of V. Then, for this, we need to find a base. because S is a set of all linear functions, we can easily find a base for all linear functions. So that is, for example, the base consists of vector 1 and x, because each linear combination we can write it down as a constant plus a constant times x, so that this is a base for subspace S. But here, these two vectors are not orthogonal. So that to do this, we need to make a orthonormal base for S. In this case, what we need to do is we need to get the length of these two vectors to make them equal to 1. For function 1 or vector u1 here is length for sure is 1. Then we need to make u2 is next 1. So in that way, 1 equal to the square of the length of u2. By definition, here we need to evaluate this integral, and we can easily say this integral get this form. And then because orthonormal, we need these two vectors are orthogonal, so that 0 equals the inner product between u2 and u1. By the definition for inner product, we need to evaluate this integral. This integral gave us the result is this. A and B here are the constant we need to find. So from the second equation, we can say B equal to negative AO2. And then once we get the B equal to negative AO2, then we substitute to the first equation. Then from the first equation, we can get A squared equal to 12. From this, we can say A equals the square root of 12, or negative square root of 12. We just pick up 1. So pick up A equals the square root of 12. That equals 2 times square root of 3. And then once we get A, then the B is negative AOT, so we get this. Then the next step is we want to find the best linear square approximation to X based on the theorem 5.5.8. So that means we need to find the projection of this vector Ex onto S. Now this, based on the theorem 5.5.8, that can be the function we want to find, we call the Px. That is a linear combination of the orthonormal base. So use the orthonormal base here, we can get the result. So Ex is the vector in V, and then U1 is the also is one of the base vector. So make inner product. That's the coefficient for U1, and for U2, the coefficient is inner product between Ex and U2. So these two vectors make inner product. And once we get that, then we can find the solution. Now take a look at this solution. We can say Px equal to, this is a scalar or just constant. And here, this here is the x term. So from this we can say this for sure is a linear function. Now this function is what we want to find. Is the best linear square approximation to the function or the vector e to the x. That's all for today.